next talk will be delivered by Seidel, and the title of it is Differentiation with respect to the Kähler parameter.
Is this working?
Yes.
Yes, okay. So thank you very much for inviting me. I'm a bit embarrassed because I don't really have any complete results to present, so this is sort of work in progress. I've been working on this with the speed of sort of a blind slug. So you know how it is when you see a slug and it's trying to get off the sidewalk into the grass. And it's not such a long way, but it's a long way for a slug. So maybe some of the younger, faster people in the area want to pick up the slug and just put me down in the grass. Maybe I wouldn't even mind that. Yeah? I'm not going to say any names. I can say names somewhere here. Anyway, so what is this about, right? So consider something like Gromov-Witten theory. So we're looking at curves, and they could have they could lie in some homology class in H2 of some manifolds, and they are counted with. Usually, you introduce some formal parameters, and in this case here, I want to introduce just one formal parameter. So the Kähler parameter, formal parameter Q, and you count them like this. Okay. And so if I start to differentiate, well, I hope we can all agree that that is the case. So there you go. So this class here, right, so it gets multiplied by this class here. So schematically, using the divisor equation, if you think about it, you have some kind of Gromov-Witten invariant, and it's associated to some kind of Riemann surface, maybe with marked points. Then what happens is if you try to differentiate it, you introduce a new marked point, and at this marked point you insert the class Q inverse omega. So omega is the Kähler. Okay? So if I've said anything that's mysterious, it's because I'm explaining it badly, not because there's anything mysterious about it. Okay? So this answers the question completely of what happens when you differentiate with respect to the Kähler parameter. So the question that I'm interested in is what if this class here that plays this particular role is itself a Gromov-Witten group, which means you have this is some cycle, and that cycle is itself represented by some family of curves. Okay, maybe you don't understand what exactly I mean by this question, but you'll see it in the course of the talk. Okay, so the fact is that this, when this is the case, this leads to certain differential equations with respect to the Kähler parameter, and I'm only interested in a specific geometric situation. But before I do the geometric situation, let me write down the kind of equations that we'll see, and then I'll explain why they're relevant. Okay? So this was the introduction. So now, the differential equations. Okay, so the basic form here of this differential equation is and this is full of notations that I will explain later. Okay, so this is a linear differential equation for two functions, rho and sigma, and both are functions of this formal parameter Q. And there are a bunch of coefficients here, psi, eta, and z2, which are also all functions of this parameter Q. Okay? And I will explain later how they appear. And psi is non-zero. So one thing that you can obviously do with a second order, a two-variable first order ODE is to try to write it down as a second order scalar ODE. And in this case, you can do it because this coefficient here is non-zero. So, so a reduction to second order gives you the following thing. So now we're reducing it to just an equation for rho. So this is psi squared. This is this mysterious Z2 thing. Rho equals to 0. So this is the scalar second order form, and then once you have rho, you can recover sigma by from the first derivative of rho and psi. The other thing that you can do is let's think about this as a you can think of this as defining a family. So think of the fundamental solution of this. Think of it as defining a formal family of automorphisms of the projective line. Okay? And then you can restrict this, think of the projective line as the affine line union infinity, and you get a differential equation for sort of motions of the affine line, essentially with some pole maybe, which is no longer linear, obviously. It's a family of projective transformations of the affine line. And so this means that if I set here, so so the relation with to the previous thing is that lambda is sigma divided by. Okay. So this is the maybe I should write it. Everything is equals to 0. Okay. So these are all forms derived from this equation here. Now that I have all the forms, I will explain where it actually appears geometrically. Okay. What's that? Excuse me? You're confused with my notation. You're right to be confused with my notation. But you will understand the notation when the things actually make an appearance geometrically. Okay? So the first time that I actually saw these equations, I actually derived them by numerical computations. Cracking up the degree out of Q up to 40 or 50, and using some smart guesses and rings of modular forms. And the example that I was working on is the example of a rational elliptic surface. Okay, so we have a rational elliptic surface over CP1. I really want to think of it as CP2 blown up at 9 points and as having the simplest possible singularities, but it doesn't really matter. Okay, so so assume for simplicity that the fiber here at infinity is smooth. So it's a smooth elliptic curve. Note that. So the first Chern class here is actually represented by this fiber here, and as far as the Kähler class is concerned, well, let's suppose this is CP2 blown up at 9 points, with obtained from a pencil of cubic on CP2. So you have the 9 exceptional sections. That's not a Kähler class, but plus some constant times the fiber. And that constant is some fixed large constant. Okay? And later I will also consider the complement of this guy here, which comes with its map. So you just remove the fiber at infinity. Okay. So this is the rational elliptic surface. what am I going to do with it? Well, I'm going to do it from of Witten theory. Okay. As usual, my notation is slightly unusual. So it's so it's enumerative geometry is extremely well known. So I want to look at just the simplest kind of enumerative geometry, namely genus zero curves with one marked point. Okay, and so the simplest kind of that you can have are sections. So there's some count of sections which I call like this. So formally speaking, you take those classes which intersect the fiber once, and for every class there's some number here. In fact, there's the cycle that you that the section spans, and then which is some multiple of A, and then you integrate this at this usual Q component. So this is an element in the second cohomology with coefficients, and this script K, that's my coefficient field. It's some field with a Q in it. I don't know what if everything is. If the form would be integral, you could take this to be the Laurent series field. If not, you have to allow fractional or real exponents of Q.
Do you mean here A times M is equal to 1? So what is
A? Excuse me. Yes, thank you very much. I don't know what I did. A times M is 1. Yeah. So these are sections, and the other non-trivial coefficients that you have is where A times M is 2. So these are bisections. But in this case here, this lies in H upper node. So this is just a single function. Okay? And in fact, this is the function here. Is there some problem? You just take, there's some H upper 2 class with like rational coefficients that are associated to this class A that are called Z sub A, and then you sum them up with Q to the usual integral. K is some ring that is a ring of formal functions in Q. Let's say if everything is integral, you could take a Laurent series ring, but in general it's not integral, so you want to take whatever, some ring of Novikov series. Okay? So this thing here is the first guy that appears in here. This is this first coefficient. Okay? The C2 here.
So Z of A is exactly what?
ZA counts the curves in homology class A with one marked point. So in practice, it's actually, in this case here, it's a multiple of A, right, of the Poincaré dual of A. Okay, I just want to say, formally you write this as this Q series. Okay. I think it's a one-pointed Gromov-Witten invariant. So don't worry too much about I'm writing it. I just wanted to remind you that there's this formal variable Q. Okay, and so the lemma that I want to say is that, what I said in the introduction is suppose that this particular class here is itself a Gromov-Witten invariant. Now I can say what I mean. Okay, so for some functions. Okay, so this class here, well, times Q inverse, because that's what I need. This guy here can be written as a linear combination of this Gromov-Witten invariant and some multiple of the fiber. Okay? So this is a little lemma. It's almost entirely straightforward because there is a sort of rich monodromy action on the cohomology of E, and this guy here and that guy here and this guy here both belong to the invariant part, but the invariant part is two-dimensional. Okay? And in fact is generated. The only thing that's kind of entering into this question is why this thing here is non-zero, right? But in fact, the lowest Q power contribution to this thing here just comes from these 9 exceptional sections. And so to lowest power, this is the exceptional locus, and this is the fiber, and therefore, of course, they generate this to lowest order, and then because there's no more space, it has to be true. What's slightly more interesting is to figure out what these functions psi and eta are, and as usual, you sort of dip immediately into fun with modular forms. But it's not relevant for this talk. So this is here. So now you know actually everything you need to understand this equation. You have this z upper 2, it's this count of bisections here, or if you like, the count of rational curves going through a given point in E bar. And the psi's and the etas are the coefficients that appear here. Okay? So you know what this, now everything that's on this board sort of makes sense. So you have these coefficients, psi, eta, and z2. So you can solve for rho and for sigma. And then the question is, what do these solutions actually mean? Okay? So, okay. So now is the question, now I've given you enough information to formulate these equations here. Now the question is, why are they relevant? Okay, so the first theorem, this is actually not a deep theorem, but consider the small quantum product with, actually, let me do it. So 1, 2, 3, then this lemma here when the number is 4, and this guy here when the number is 5. So consider a small quantum with the fiber, which I remind you is this guy here. So the small quantum product with the fiber is an endomorphism of the cohomology okay, so then its eigenvalues are solutions. Okay? So the cohomology here is 12 dimensional. So you get with multiplicity, you get 12 eigenvalues. In fact, what happens is that you really get only 4 because 1 has multiplicity 9. So independence of this parameter cube, these 4 points on P1 move around. But in fact, they all move around by a single conformal transformation, so the cross ratio is preserved. And the conformal transformation is exactly that given by that family, or in other words, they satisfy this one. Okay. And this is actually not at all hard to prove. So here's another theorem, which is related. So let L in E, I'm sorry, I didn't have enough space to keep all the notation on the board. E is the things that are disjoint from the fiber at infinity. E, a compact Lagrangian submanifold. With 0 Maslov class. So actually, there's some. I'm not stating this theorem completely, so I'm going to put it in quotes because there's some technical assumptions. So the count of Maslov index 2 disks in E bar comma L. So you consider now disks that are allowed to go into E bar, and because of Maslov index 2, they go into E bar, they intersect the fiber at infinity once. So you can count how many of those go through a given point of L, and that gives you a series in Q. So is a solution of this equation. Okay, so that's why I called it. Yeah. So again, as you know, you have this for these Lagrangian submanifolds, you have a sort of a function of Q associated with that, which is sometimes called the value of the superpotential at that Lagrangian submanifold. And that is a function of Q, but it's not an arbitrary function of Q. It's a solution of this differential equation. Now, these two theorems are actually related. If the Lagrangian submanifold is, if the Lagrangian submanifold has non-zero homology class in E bar, right, then it is known that the homology class is an eigenvector. And the eigenvalue is actually equal to this function here. This must have the two index discounts. It's sort of open-closed formalism. But this also applies if this is null homologous. Okay, so this one here is actually simple enough that I can give you. I mean, so I didn't state it exactly because, you know, in order to define this count of Maslov index 2 disks, you need to do some technical work. But to the same level extent, I would like to give you a sort of proof. Okay, and then you'll see how this is possible. So, you know, for the purposes of that proof, maybe, you know, this one here is not so important. Maybe even this one here is not so important. The important thing is that it's a differential equation that has the form the derivative of something is its square. Okay, so our question is, where does this come from? Okay, so the count of Maslov index 2 disks, I do like this. So I consider the disks which have boundary on here, well, I will put maybe a 1 in here. So this guy here, this is half the Maslov index. I put these numbers here in these brackets. Now, one thing that I like to do is, even though this is a perfectly well-defined count as it is, the domain, which is just a disk array, we should put in a marked point on the boundary because we're counting disks that are going through a fixed point on L. This is not a stable domain. So I will stabilize it by putting a marked point, and I will ask this marked point to go through a fiber. So we'll do a fiber infinity or something. And this changes nothing because every disk goes to the fiber at infinity once, but it gives me a stable domain. Okay. So I will insert and remove these things at my leisure. Okay, so now, what happens if I take this count and I differentiate it d by dq? Well, it's the same procedure as I explained before. So well, in principle, there would be this fiber here. And then there's another marked point here, which is carries this q inverse. Okay? So this is essentially, this is just the divisor equation, and it's just as true in this situation here. And again, these things are sections. So this is this formalism that I showed right at the beginning, where if you differentiate by q, you insert an additional marked point. That marked point can actually be anywhere on this disk here. Okay. And so, well, at this point here, I can actually remove my original marked point if you want. So, because I don't need it anymore to stabilize. So this is what the situation looks like. Okay? And again, these are still sections. Okay. So, excuse me. So now I will actually use my assumption, which was that this class here, so now this is equal to this guy here. So there's L, there's my marked point here, marked boundary point here. And now this thing here is the same thing as, so this class here can now be expressed as psi times this guy here, essentially. So this is Z1, this evaluation of section. This is a sphere. Right? And now, as usual, because I like to stabilize things, so this is 1, 1. And I will put in 2 marked points, which each have to go through a fiber, which changes nothing, just to make this into a stable domain. So this would be the case if this guy here was actually equal to psi times C1, but there is it's also, you know, this guy here, Q inverse omega E, is given by this Gromov-Witten theorem plus a difference, which is actually just going here. Here you just put in a fiber. So eta times M, and there we are. Okay. So this guy here, you actually know. This is just minus eta times lambda. So this is again, this gives me again the count of disks. So this is the first term here that I was advertising. I had the derivative in Q of the count of disks. I get this guy here. Then I have now it's a question of this quadratic guy here. So I write this gentleman here by gluing these two things together. So I get a disk. Now this has the degree of 2 over the base, and there are two things where it intersects the fiber. Okay, and so then you pull those 2 points apart here, and you get two disks glued together at the boundary, and so it gives you this count that you had squared minus eta times this count. Okay, so these are these two things here, the square minus eta, and then the question, wait a second, how about this guy here, right? Well, you have to be a little bit careful here. So here we have done a degeneration where we bring these two marked points together. This guy has degree 2 over the base. This is one possibility, that you have degree 1 and 1, but that's not the only possibility. You could have degree 0 over the base here, which means this is a constant disk, and you could have degree 2. Okay, so you have to subtract that. And now I ran out of space, so I have to, up here I have to subtract that. Minus psi times, well, essentially this is a constant. So it counts as 1, and here you have this thing here, which are this fiber, and this has degree 2, okay? And so the degree 2 things are counted by this Z upper 2, because they have degree 2, there are, you know, the divisor equation adds a 4 when you put in these additional things, and so you have minus 4 psi. Okay? And so this is the proof of this sort of proof of this theorem of accounting Maslow index 2 disks. Where did I suppress the technical things? Well, when I said, you know, here it's a Maslow index 0 disk that's left, and therefore it's constant. I'm actually kind of assuming that there are no Maslow index 0 disks. In general, you have to sort of make there's some algebraic formalism when you make this L into an object of the Fukaya category, where you kind of cancel out the degree 2, the Maslow index 0 homomorphic disks by some algebraic counter terms. Anyway, this thing here, I think you can at least get a picture of what's going on. Okay, so we saw that this equation here appears in Gromov-Witten theory and in open Gromov-Witten theory. In this case here, actually, I'm not actually all that interested in this thing here. So. So what I'm actually looking at is a different story that I'm interested in, which involves the geometry of the fiber. In this case here, the elliptic curve. Okay, so. Unfortunately, the way that I set up so what I want to look at is I want to look at the fundamental solution of this guy here. Unfortunately, the way that I just set it up, while it's easy to formulate, it's not so practical, because this psi's and etas, the way that I set it up, necessarily involve negative powers of Q. Now, you could actually choose the symplectic form, even though it's not really a Kähler form, to just be the exceptional locus and forget adding a multiple of the fiber. And in that case, so we can consider. So just basically you multiply everything by certain powers of q, and in that case, you actually have that these things here are, this has 1 plus a positive power of q, and this thing has only positive powers of q, and we can consider the fundamental solution. So theta, so it's some matrix. So which means that, you know, theta of 0 is the identity, and it's the unique solution of this equation here. And then the theorem says, so let B inside. Now I'm looking at the geometry of the fiber. There's no interesting Gromov-Witten invariance of the fiber, but I can look at the Fukaya category, be the subcategory of vanishing cycles. So we have this, you know, we have this pencil of elliptic curves, and it has vanishing cycles, which are circles. We consider the full subcategory of this. So then B is defined over. So usually B is defined, you know, is defined over this field here of formal series in Q, but actually it's defined over a polynomial subfield C, T, where T is theta 1, 2 divided by theta 1. Okay? So it's polynomial, excuse me? K is the Novikov field. Yeah. So it's actually defined over a polynomial subfield in one variable. So in this case here, you can sort of, you know, of course the Fukaya category of the elliptic curve is extremely well known, and you can see what this subcategory is, and this thing here, theta 1, 2 divided by theta 1, 1, is the mirror map for a particular family of elliptic curves. And moreover, it's a mirror map where the mirror family of elliptic curves is a rational pencil, and therefore the category is kind of polynomial. But I didn't get in to this mirror map in the ordinary way, which is by a Hodge theory and, you know, Gauss-Manin connections and so on and so on. But it just appears in here. So okay, so this is as far as it goes for the pencil of elliptic curves. So the rational elliptic surface. What is the general situation that's going on here? So.
Is this the geometric meaning of 1, or you stated the geometric meaning?
Yeah, this is one of the geometric meanings of 1. Okay. This is why. Yeah. So this is the geometric meaning of 1. Okay. So here you don't see the projected version directly, but you see this thing here. In fact, the first row of this thing. So that's right. So essentially, it in this case here, that gives you back the mirror map. And
so there was no other meaning of 1 so far?
So far, no. In fact, there are more, but I will never explain. Sorry. So the general picture is that of anticanonical Lefschetz pencils. Okay, so I start with such a pencil. On a smooth Fano variety, and I blow up the base locus to get this guy here, which is called the graph of the pencil. So it's a family of Calabi-Yaos over CP1. I need the base, for this to be nice, I need the base locus to be smooth, and then in my mind I might just as well assume that it's a Lefschetz pencil. So you get this guy here, and then you get E. And so what do these things? So remember we had this lemma that I called 4, which said that Q inverse omega E bar is psi times C1 minus eta times the fiber. Okay. Well, there's no reason why this should be true in general. So how we turn this into assumption? We assume that this is true. Oh my God, can I actually do this? Well, it's always true if for the same reason as some reasons as before, if, for instance, my original Fano had second Betti number 1. And it's also true in more general case, you can apply some symmetry arguments. But actually, there's a much better idea, which is that if you allow yourself to sort of deform the situation by choosing appropriate B fields, and therefore deforming the count, you can actually make it hold always for some deformed situation. But let's assume, so this is going to be the assumption that is going on. So this is no longer a theorem, it's just an assumption. Okay, so then, so theorem 5 about the eigenvalues of quantum multiplication is always true under this assumption here now. So they are all, now you have these functions, so they're all, the eigenvalues are all solutions of this. Well, this theorem 6 about about counting disks, well, it's true-ish to the extent that, technically it's very complicated to get everything up and running, and once you get everything up and running, it seems like the same argument should go through, but, I have not carried out all the technical work that's necessary to do this discount. And how about this guy here, this last one that I haven't given a number, and I will now give you the number 7. So how about this guy here, theorem 7? Well, it's a conjecture. Okay, so but this is where the actual interest in the whole subject comes from. This is what I call the polynomiality conjecture for Fukaya categories of Calabi-Yau hypersurfaces, right? So it says that yes, you look at the enumerative geometry of the graph and you solve this equation, and then this gives you this particular single variable mirror map. And after applying this, it will be polynomial, polynomially dependent on one variable. In fact, this is a sort of coarse version. There's a much more precise version which tells you pretty much exactly what this Fukaya category is in its Q behavior. Well, if you understand what it is at Q equals 0, it tells you exactly how it deforms. So, of course, this is the first year that I think Maxime is not here. When I'm talking, it would immediately say that this is I should say that this is a consequence of homological mirror symmetry. This conjecture here. Well, indeed, in some cases where you can, you can use homological mirror symmetry, just essentially like I did for the elliptic curve, more or less, to prove that this is actually correct to some sense. But the point is, this is supposed to be true in general, and not dependent on whether you know homological mirror symmetry. It's a statement about Fukaya categories that is supposed to be independent of whether you understand the Fukaya category exactly or not. Okay, so, right. Okay. How much time did I actually use?
You got 20 minutes.
Was that?
You got 20 minutes.
I have 20 minutes. So can you tell me when I got 5 minutes? Okay. So, questions, anybody? Because now it's going to switch into slightly different mode. Okay, so I've explained to you, what the letters here mean, and I've explained to you how to write down these equations and what their implications are supposed to be. But I didn't actually explain to you anything about, why these equations should occur. Where do they actually come from? Okay. So now I'm going to switch gears, and I will explain to you how you can get. How differentiation with respect to the Kähler parameter can be made part of a suitable formal framework in which you can see why these things would occur. And at first, the framework is going to be, this is actually sort of general, and then it will have to be applied to this particular geometric situation. Okay? So, and it's a framework of suitable topological quantum field theory. Okay. So, so what is this? What is this quantum? What is this quantum field theory? What does it have? Well, you have a circle, and it's a parametrized circle. So I indicate this by putting a mark point, and you want to associate to this a graded vector space. And then if I have a surface, and I'm going to restrict to genus 0 surfaces here, because I don't need any more, with one, and so they have genus 0 surfaces. They have certain amount of boundary components. Every boundary component is parametrized, which I denote by putting a marker on this thing here. And there is exactly one boundary component which is an output, and as many as you want as inputs. Okay. And so this gives me, for instance, in this case here, so this gives me an operation which goes from as many inputs that I have in here into the output, and similarly for families of surfaces over a closed oriented base P, so some real manifold, and you have some differentiable family of Riemann surfaces, all of this kind. So if you have such a family, you get a map as many inputs as you have into the output, and the degree of this map is minus the dimension of your family. And so finally, allow one additional interior mark point so if you have this, you don't have to have it, and in principle you could have several ones, but at the moment I will only need one. So you could have some. Usually when you have such a mark point, there's a bunch of different choices of things that you can insert in here, but I will only allow one particular insertion. And so therefore, that gives me an operation that, so it's the same thing, and it has this thing here, the insertion is of degree 2, so it's got minus 2 extension. Okay. And there are various TQFT rules. Okay. So, and so the outcome is a version of sort of Kähler's analysis. So Kähler analyzed the algebraic structures that you get without this additional mark point in the early 90s, and so the outcome is that, well, there are some certain basic operations. So this the pair of pens product, which is just a single surface, and it's a commutative unital with unit this guy here. The other thing that you have is you have a natural one parameter family, but the markers always point up, but these two circles move around each other. That gives rise to a bracket. And these two things together make it into a Gerstenhaber algebra. And you have now the family where you have like an annulus, but you move one of the markers around, so it's again a one parameter family, and it gives you the BV operator, which makes this into a BV algebra. Okay? So so this is H, the structure of a BV algebra. So you can obviously combine these operations in various ways. In fact, one of them is redundant because you can reconstruct the bracket from the product. Okay. Now I haven't put in the additional marked point yet, so the simplest way is to do like this. You put in the additional internal marker, that gives me a class. And that class is actually annihilated by the BV operator, because if you glue this thing into that annulus, you will get the same kind of structure where it's if you glue that into the annulus, you will get the same kind of structure where this point here is supposed to wander around, but that's not really a family because wandering around can be compensated just by rotating this thing here. Okay? And the other thing that I would like, again, there's something that is worthwhile mentioning, even though it's derived from this thing here. So take an annulus here and let the mark point wander around in a circle. So this gives you a map of degree -1, which is, in fact, you can show is just the bracket with this particular element S. But just like I gave you both the bracket and the BV operator, so it's redundant, I like to give you the element S and I like to give you this map. Okay? Okay, and so
What is the dimension of H?
of what?
H.
No, H is a graded vector space.
And it gives a structure. What the dimension of the vector? It's infinite dimension?
Oh, it's, well, in my case, it's usually infinite dimensional. But, yes. But, I didn't say anything about whether it was infinite dimensional or not. It's usually infinite dimensional. Okay, well, in my applications. Okay, so, so this is not so far terribly exciting.
Can you explain the bracket again?
The bracket is just, you take these guys here, this has 2 inputs and an output, okay? And you take these 2 input circles and you move them around each other and make a full rotation while having the markers point up, okay? The reason why I have to say while having the markers point up is because unfortunately we have this delta. So whenever you have operations of negative degree, there are various versions where you add, things with delta in them. So the one that I want is this one. Okay. So, okay, so there are, this is not exciting and it's not going to get me where I want. So I want to introduce 2 refinements. And so consider, so now we consider H as the cohomology of some complex with chain level operations. I think this used to be called a topological conformal field theory, but now I think it's just called a topological field theory. So there are chain level versions of all these operations. There are chain maps. The difference is that the relations that you previously had, such as delta squared is 0, or the Jacobi relation or something, will hold only up to chain homotopy. Okay? So I have the same basic operations. But additional homotopies.
Do you take the homology or the complex of
Complex of chains, yes. Now, H is the cohomology of some chain complex, okay? And now I'm assuming that you have operations on this chain complex that come from chains in the space of Riemann surfaces. Okay, and we have additional homotopies. So for instance, we still have, so e.g. Now, I'm going to use the same notation, so I know this is cool. So we have this element S, which is closed. But now, if you consider this guy here, it's actually no longer identically 0 because you have to make this argument with a homotopy. but there will be it will be d sigma for some distinguished sigma in Caesar, and so on. Okay, so this is a pretty standard modification working on the chain level, not actually what I'm interested in. So, okay, so the second modification that I want to do now involves differentiation with respect to the Kähler parameter. So far there wasn't a Kähler parameter here. Okay, now assume, so this C star D is over K and carries a connection so this is an operator that's not linear over K, so it satisfies, so it's a connection in Q direction, so it satisfies this guy here. Okay, so why do I put a slash through this connection? Well, because I want to remember something. This is a chain complex. Okay, so this is not actually a connection on the chain complex. It's not compatible with the differential. In fact, instead, what I want is that the failure of it to commute is this, so dx minus the connection here. So this thing here, you can see easily. This is actually a K-linear operator of degree 1. This thing here is -1 of degree 1, and the axiom. So this is a new axiom. Okay. So the way that I would like you to think about this axiom is, I would like you to think of the differential as the operation associated to the -1 dimensional moduli space that is an infinite cylinder divided by the translation by R. Okay, and then the axiom says that if you want to measure how this is compatible with the connection, you're supposed to insert this mark point here. And since I'm portioning out by translation, it doesn't matter where you insert the mark point in that direction, but there's 1 degree of freedom in this direction. Okay. And similarly, if you want to see how, let me write it schematically. If you want to see how any operation commutes with this connection here, that is going to be given by the same operation with a mark point and where the mark point is inserted anywhere. Okay? So this was the same thing that we saw in Gromov-Witten theory and when counting holomorphic disks, where this additional mark point carried this class Q inverse omega, and now I've axiomatized this, in some kind of abstract framework where you have this operation. These are my axioms, the new axioms of the theory. Okay? It says this chain complex now carries this differentiation operator, and for those people who are symplectic, topologists, no big deal, right? I mean, the chain complex underlying flow cohomology has a distinguished basis, and therefore you can write down the trivial operator in that basis here, differentiation by dq. But it's not compatible with the differential, of course. In fact, its failure to be compatible with differential is exactly given by this count here. Okay. So this is my formal framework, and so now, in this formal framework, various things happen. I would like to. Okay, so what's happening here? So the failure of D to commute with this with the derivative is given by R. Now, in the cohomological framework, R was just a bracket with S. Here, it's not quite true because on the chain level, R is chain homotopy to the bracket with S. But you can use that chain homotopy to modify this connection here, and then you get a connection whose failure to commute with the derivative is just the bracket with S. Okay? So this element S is now, you can think of, in fact, you would better think of it as a Kodaira-Spencer class. It's the obstruction to us being able to move in dq direction. Okay? So this is this framework here, and now I'm going to introduce.
So you have about 5 minutes.
Yeah. Thank you. Now I'm going to introduce an additional assumption, which is the following one. That this thing here is 0. Okay. So concretely, on the chain level, for some choice of alpha. Okay? So this is an additional assumption that's not part of this general class of theories. It singles out a very specific subclass of theories. And since that was the obstruction, the sort of Codano-Spencer class, trivialization of the Codano-Spencer class should allow us to move in Q space. And in fact it does. So note this. Note we then get so this thing here is obviously this is not closed, so this does not have a cohomology class, but you can say the following thing: if I apply the BV operator of this thing here, then what is D of that? Well, D of that is essentially the BV operator applied is the BV operator applied to S, so I can kill it with this guy here. So we get a class in H upper 1, which depends on the choice of alpha. So if you change alpha by some, well, we get a class in H upper. Yes, I got a class in H upper 0. So if you change alpha by some something that's cocycle, you add some cocycle to this, then this A will change by the BV image of that cocycle. Okay, so this is some class. But now, this is the first implication, but more importantly, so I guess in the numbering, I should call this assumption 8. The following theorem. If 8 holds, H star can be equipped with a connection in Q direction, an honest connection. Okay. Now you're not surprised because, as I said before, S is the obstruction to that. So if S vanishes, you better have a connection. Okay. So which is compatible with the product and the bracket. Okay? So which means that this connection is a derivation for both the product and the bracket. And now, what about the BV operator? Okay? So I said that the class S is 0, but if you know these kind of theories, I didn't actually say that the class S was equivariantly 0. Okay? And satisfies. So if you want to see what this guy here is, so this is on the cohomology level, X in H star. That is just given by the bracket with A. Okay. So this is somewhat odd. You have a connection that is compatible with the product and the bracket, but it's not compatible with the BV structure. Instead, the BV structure changes in this well-measured way. Okay, and so note. So we have a family of connections. Which are like this. You have this guy here, and you take some, so C is some scalar. You subtract some scalar multiple of the product with A. That gives you a whole family of connections. Now, delta minus 1 is compatible with the BV operator. So the nabla 0 was our previous one, nabla minus 1 is compatible with the BV operator. That actually follows from this, but I don't have time to write down the two lines that it needs, but no. Okay, and so, so the reason why this strange phenomenon happens here is sort of best explained from a sort of, categorical framework. So if you add boundary data to your theory, then you can think of this H star as either Hochschild cohomology or Hochschild homology. And if it's Hochschild cohomology, the product and the bracket are natural, and the connection you want to look at it is nabla 0. If it's Hochschild homology, then the BV operator is natural, and you want to look at nabla minus 1. But I completely ran out of time. So what is the consequence for the geometry here? So now we return to this to the previous geometric thing. Of these things that come from anti-canonical left-shaped pencils. So we had these guys here, and I had this. Okay, and in this case here, this H that I want to look at is something called the symplectic cohomology of E. It comes with a map from the ordinary cohomology, the acceleration map. Acceleration. So you want to take the class here, the symplectic class of this guy here, which is non-zero, in here, and that will map to this element S. That's how the framework will be constructed. Okay, and so now you notice that my whole theory that I built is based on was based on the assumption that this class here was 0. Which seems a rather bold assumption, because certainly the cohomology class of the symplectic form is never 0. But there is a simple lemma, which is that, so Z1, this is a cohomology class in E bar. If you restrict it to E, lies in the kernel of the acceleration. Actually, traces of this go back in the literature more than 15 years, just nobody seemed to notice. So the consequence is that, so hence, assumption, so the original assumption 4, which was that you could write this guy here as psi times V1 minus eta times the fiber, implies the vanishing of this. Okay? So this condition that I put into this theory abstractly holds in this case here. If this assumption is satisfied, just if you take this guy here and you restrict it to E, this term will go away. Psi is non-zero, you divide out, and it turns out, well, you don't have to divide out. This thing here, and it turns out that this guy here must be in the kernel of the acceleration. Okay? So this implies this. So this means that now you can get a connection on symplectic cohomology in Q direction. And you can look at various things, and I probably ran out of time. So I will just not try to explain things too well, but the conjecture is that so the class E, which is the identity, which is the image of 1, satisfies the differential equation 2. So this is the second order equation with dq replaced by this connection here. Okay, so maybe you forgot everything about where this comes from, but basically I started out with this first order equation and I wrote it as a scalar second order equation And the claim is that this second order equation appears in this context if you try to apply this differential operator to the unit class. So the
Nabla minus 1?
no, it's actually nabla 1.
So
And
you didn't talk about Nabla 1.
I did not talk about nabla 1. So nabla minus 1 is responsible for natural transformations from the identity to the Serre functor, but nabla 1 is responsible for natural transformations from the Serre functor to the identity. And this is in fact the one that has to occur here. Thank you very much.
Any comments or questions?
Is there any preliminary statement on that?
Is there any what?
Preliminary statement.
For what?
Form Carola or connection or something.
Well, so the idea is that once you have this and you have a suitable open-closed string formalism, you should be able to derive the polynomiality conjecture. It's a long way from the slug. I don't actually even
All right.
approximately understand each of the steps involved.
If there are no more questions, let's thank Paul again.